I-1151. So now we're going to be looking at exponential functions. And really the focus question here is like, how do we describe something that keeps doubling mathematically? In this case, I have a picture of cells that are dividing that I stole from online, which you can find the reference down at the bottom of the PowerPoint. Now, the generalization to this, because something might keep doubling, or it might keep tripling, or it might only go up by a little tiny bit. The generalization is, how do we describe something that keeps changing by the same proportion? So in this particular case, we see from looking at this investment, say, for example, it went up by about 50% the first time, and then it went up by 50% the second time. So we can say that it went up by a proportion of 50%. Remember that a percentage is a fraction out of out of 100. Sorry. And then also we have radioactive decay, which in this case it doesn't add 50%. In this case we're going to be losing half of it every single time it goes through one full half-life. And so this would be that we are subtracting 50%. So we're going down by a consistent proportion, but it's still changing either positive or negative by this consistent proportion every single time. So let's look at the fundamentals and the graphs, and then we'll end on a checkpoint before we get to the next video. So if I were to start with something, let's say we were in a pandemic, and we had a disease that might spread from one person to two. Well, in the first generation, it might spread from 1 to 2, but then each of those 2 people would spread it to 2 other people, so you get 4, and then 8, and so on. So you get this doubling kind of effect. So if we were to write down a table, our starting population, let's say, was 1, and then that 1 person spread to 2, 2 to 4, and yada yada. Now that would look like this graph that I have right here. So it goes up really quickly. Now, that's assuming that we say that our starting point is at the origin, which is at a time or x equal to 0. Now, if we were to describe this mathematically, it would be something like this. Like the function would look something like this. I'm using C for COVID, let's say. So early on in the pandemic, it might have grown like this. So if I did, x was equal to 0, then 2 to the power of 0 is equal to 1. And you should refresh yourself on exponentials or exponents if that doesn't make any sense. And then if x was equal to 1, 2 to the 1 would equal 2, and so forth. So I can verify that this function right here matches the behavior I'm seeing in my table. Now, what I've left out here is that there is a number that's multiplying this 2 to the x. I can rewrite this as 1 multiplied by 2 to the x. And that 1 is giving me my initial population. So the general form of it would be up here, where that number that I'm multiplying by, which I've labeled as capital A, doesn't matter what you label it as. It might be, actually often you say that that's the population at x is equal to 0. So in this case, y is equal to y0 times your base of the exponential to the power of x. So a, or y naught, or whatever it is your initial population, and your reproductive rate, or how much this disease is spreading, is given by the base of the exponential. So in this case, our base was 2. Now, not every disease spreads the same way. Measles can hang around in a room quite a bit longer than COVID, and so measles has a reproductive rate of about 15. So every 1 person might infect 15 others. Now, if you had a measles outbreak and you had a population of 100 people when you first noticed that there was an outbreak, then those 100 would each give it to 15 people, so you'd end up with 1,500. Or let's say we were to look at, I left this up. If we were to look at the second generation, then if I go through the math, 100 times 15, and then this is to the power of 2, that gives me 22,500 in my second generation. By the way, note that I use the parentheses just to avoid any confusion. It's a good habit using your calculator, even if you know how it deals with the order of operations, just to use parentheses all the time. So so in this particular case, you start with 100 people, and then you have a reproductive rate of 15, and that would be another exponential function. Now, the reproductive rate, or the base of the exponential, when you're looking at something like disease, there's a lot of things that can play into there. If you have one person with a disease who quarantines completely and doesn't see a soul, they're unlikely to spread that to somebody else. Whereas somebody who may be asymptomatic and in a very high population density area, they might be able to spread it to 10 people. So what the reproductive rate is for a disease isn't really something that's fixed, even though I said 2 and 15. It can change over time. So this is a graph that I got from this website right here, looking at how in the COVID pandemic it changed up until July of 2021. And so early on you can see that there was a really high reproductive rate, but then with different public health initiatives, they were able to reduce it. And so I might ask you to think about what are at least a couple of factors that might change the effective reproductive rate of something like COVID in a pandemic. What's interesting is that right here at the end, and I'll zoom in a little bit, we get the world at this point has an overall reproductive rate of about 1.05, whereas Canada has a reproductive rate of about 0.91. Now, we know that these are both showing that there's a proportion of people, the proportion of people who are getting the disease for every generation is increasing by a certain percentage, increasing consistently. Actually, the proportion is staying the same. The number of people is increasing by the same proportion every single time. So if I were to look at the world, and just for shorthand, I'm going to use the world number of infected is proportional to 1.05 to the x, and I might rewrite this as 1 plus 0.05 to the x. And so that's like plus 5% every single time. Whereas at this point in time, Canada has a reproductive rate of about 0.91 to the x, which I can rewrite as 1 minus 0.09 to the x. So for every generation, the disease is losing ground by about 9% of the total population of the infected people. Now, what I wanted to highlight here is the behavior of these graphs and how they might change. So the top graph over here is our 2 to the x that we were looking at before, and that looks kind of like what we had written down from the table. Our 1.05 to the x. That looks pretty low. It doesn't look the same as that 2 to the x, at least not on the same scale. But if I squish my horizontal scale and I look at something like 10 times the number of generations, you can see that it follows the same sort of swooping up kind of behavior for an exponential function. What's different now is for this Canadian context at the 1st of July in 2021, when our reproductive rate was 0.91. We were losing 9% of the infected population. The 9% were clearing. When I compare from one generation to the next generation is 9% lower than that first generation in terms of the number of people infected. So in this case, we're losing a consistent proportion, and so we get this exponential decay, and it'll slowly go towards 0. So the exponential growth is on top and decay is on bottom. And they look a little bit different in terms of how they behave as you go on in time. So I'd like you to take a break and answer these checkpoint questions using the 2 graphs I've written there. Really the key thing I want you to get is if you had a graph of an exponential function, what is this going to tell you? How do you get the equation of the exponential function from its graph? So there's something that you can do without doing any calculations, but there's a hint that you're going to need to do some calculations to get the other parameter. So the 2 parameters being your initial population and whatever the base of the exponential is.